Welcome back. Today I want to talk about the rules of differentiation, and now we're going to start getting into how to make differentiation a little easier on ourselves and how can we compute derivatives a little quicker. And so the first thing I want to look at is if we have a constant function. Okay, so let's say we have a function like f of x is equal to, let's say, 3. So it's just a constant function. And what does a function like this look like? It just is, if this is my x and y axis and this is 3 up here, then it's just this horizontal line right here. And so if I were to compute the derivative f prime of x, what would we expect it to be? Well, what's the slope at any point along this horizontal line? I think everybody would agree that at some point right here on this horizontal line, the slope is 0. The slope's always 0. So we would expect that this derivative be 0. And that actually is the case. How would we actually compute this if we wanted to know what the slope was and we couldn't just look at the picture and see that it's always 0? Well, what I could do is, let's think about this in general terms, that if f of x is equal to k, where k is constant, then the derivative f prime of x is equal to the limit as h goes to 0 of f of x plus h. Well, f of x plus h, f of anything is k, because this is just a constant function. So this is f of x plus h, which is k, minus f of x, which is k, over h. But k minus k is 0, so we have 0 over h. H is not 0, so this is just 0. So f prime of x is 0 for any constant function we can come up with. So if f of x is equal to just a number, like 3 or 7 or pi or anything like that, then the derivative of that function has to be 0. All right, now what I want to look at is what if we have f of x is equal to some power of x. So let's say x to the nth power. All right, so what would be the derivative of this function? And the way that we always find derivatives if we don't know what to do is we go back and we compute the limit of the difference quotient. So that's what we're going to do here. And so I'm going to say if I want to find f prime of x, then I need to take the limit as h goes to 0 of f of x plus h minus f of x all over h. And in this case, that's the limit as h goes to 0 of f of x plus h is just x plus h to the nth power. Because my function is whatever I plug in this case x plus h to the n, minus f of x, but f of x is x to the n all over h. Okay, so this isn't like the nicest thing I've ever seen because I have this x plus h raised to the nth power, and if I were going to multiply that out, I'd have to write x plus h out n times and then FOIL all of that out, which would be a big mess. But what I'm going to do is I'm going to kind of like think about it a little bit and hopefully make life a little bit easier on myself. So let's move up here. And I'm going to rewrite, this is the limit as h goes to 0 of x plus h to the nth power. Now, I can't multiply this all out. I'm not exactly sure what it would be, but what I can do is I can get a few terms. And so what would be the very first term of this thing if I were multiplying all the x's together? So it's x plus h times x plus h times x plus h times x plus h in times. And if I just took x times x times x times x times x in times, then I'm going to get an x to the n out of that. Secondly, if I have x plus h written out in times, then I'm going to get a term that has x to the n minus 1 times h. And how many of these will I get? Well, I could, if I wrote this all out, let me do it real quick. So I have x plus h times x plus h times x plus h, and so on, times x plus h. And so let's say there are n of these. Well, how many different ways can I choose one of the h's to multiply by the rest of the x's? Well, I could choose this h to multiply by all the x's, or this one, or this one, or this one, and there are n of them. So how many x to the n minus 1 times h's are there? Well, there would be n of them, plus some stuff, and then finally the very last thing that I'd get, so I'd get the next term would have an x to the n minus 2 times h squared, and so on, and the very last thing I would get is h to the nth power. And then finally, I still have this term at the end, minus x to the n all over h. Notice that on the top, I have an x to the n, and I have a minus x to the n, and they would cancel. And what's left over? Well, I get the limit as h goes to 0 of, notice something here, is that I have this dot, dot, dot in here, but everything in there has at least one h in it. Because this one has an h term, the next term would have an h squared, the next an h cubed, and finally this one has an h to the n. So if I factored out one h on top, then I'd have an h times this first term, which I'll write as n x to the n minus 1, plus everything else. Well, everything else, the next one had an h squared, this one has an h to the n, and they're all powers of h that are bigger than 1, so they all have an h in it. So I'm going to kind of be very non-mathematical here and say that this is the h stuff. So it's h times n x to the n minus 1 plus a bunch of stuff that has an h in it, all divided by an h. Well, now, since h is going to 0, we know h is not 0, so these h's cancel, and I'm left with the limit as h goes to 0 of n x to the n minus 1 plus all of this h stuff. And as h goes to 0, all of the stuff that has h in it goes to 0. And I'm left with nx to the n minus 1. And so what I just did is I just calculated the derivative of the function x to the n. And what I found that it was is it's nx to the n minus 1. So let me write this down one more time so that we can remember. And that is if f of x is equal to x to the nth power, then f prime of x is equal to nx to the n minus 1. All right, and so this is what we call the power rule. For derivatives. That if f of x is x to the nth power, then f prime of x is nx to the n minus 1. And n could be, at this point, any positive integer. We haven't proved it yet for negative integers or fractions or things of this sort. It ends up that it does work for negative numbers and fractions and things. We'll prove that maybe a little later. But for now, what you need to know is this power rule, and that's very helpful. Two more important rules of differentiation are the sum rule and the constant multiple rule. Let's start with the constant multiple rule, and that is that if f of x is equal to some constant, let's call it k, times a function g of x, then f prime of x, the derivative, is equal to k times g prime of x. So in other words, if there's just a number like 3 or 7 or something sitting out in front of your function, then the derivative, you can just take the derivative of the function itself and you can just leave the constant alone as long as it's multiplied. Okay? A good quick example of this is if I have like f of x is equal to 7x cubed. We just learned the power rule. So the derivative, because of the constant multiple rule, would just be, well, the 7 just kind of stays because of the constant multiple rule. And then the derivative of x cubed, we know by the power rule, is 3x squared. So the derivative, f prime of x, is just 21x squared. Okay? And that comes straight from the constant multiple rule. So this is the constant multiple rule. So if you have a function that's a constant times another function, just leave the constant alone and take the derivative of the function that it's multiplied by, and you get the derivative. That's very nice. Okay, the second one that I want to talk to you about is called the sum rule. And the sum rule says the following. If f of x is equal to g of x plus, let's say, h of x, then f prime of x is equal to g prime of x plus h prime of x. In other words, if I have something like f of x is equal to x to the 7th plus x to the 6th, then we know that f prime of x is equal to, well, these are two functions added together, so I can take the derivative of each one separately. Let's do it. The derivative of x to the 7th by the power rule is 7x to the 6th, and the derivative of x to the 6th is 6x to the 5th. And so we easily, using the sum rule, I can just take the derivative of each one of these terms separately, get my derivative, and we're done. Okay? So that's how we use the sum rule. Let's move on for a second and talk about another important derivative. Okay, two more things and then we're ready to look at some example problems. The first thing is a very simple derivative that everyone should know is that the derivative of e to the x is e to the x. So this is called the exponential function, and it's kind of actually almost amazing, right? That there's a function that exists whose slope at every point is its functional value. Okay, so that's the exponential function, and if you look in any calculus book, you can see the proof of this. By the way, all of these rules that I've been giving to you, they're not magical. You just find all these results by using the limit of the difference quotient. And so you could go through and prove the sum rule. You could go through and prove the constant multiple rule. You could prove that the derivative of e to the x is e to the x. All of this is just the limit of a difference quotient. But now that we know that the derivative of e to the x is e to the x, we can use this in problems, and we will use exponentials a lot going forward in calculus. Now, the one last thing I want to tell you about, other than that the derivative of e to the x is always just e to the x, is the following. That we can talk about, we already said before, that if I have a function f of x, so this is my function, that we can talk about its derivative, and we call the derivative f prime of x. Well, what if we were to take the derivative of the derivative? Okay, if I took the derivative of the derivative, then we get what we call the second derivative. And the second derivative we write as f double prime of x. So what I mean by a second derivative is I took the derivative of the derivative. Okay, and so I get f double prime of x. Well, I could keep going here. We could talk about the third derivative. And I just call that f triple prime of x. Now, it gets kind of old writing these prime symbols. So after triple prime, we don't write them anymore. So if I took a fourth derivative, then I don't write f prime, 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 prime. I write a little parentheses and write a 4 up here. And so this is the fourth derivative of f. And the fourth derivative is the derivative of the third derivative. And you get the idea. Now, so this is one notation, but we know we have different ways of writing derivatives. So another way you could think about this is if you wrote this as y, you could say this is y prime, or y double prime, y triple prime, and y with 4 primes. This typically isn't that nice because this is confusing where you're saying y to the fourth or y's fourth prime. So this is kind of bad notation, which is why we would usually use this notation. But another notation that we use for derivatives is we could say we have y, then we write dy over dx for the derivative. So the second derivative in this case we would write d squared y over dx squared. And I've got to admit, when I took Calculus 1 for the first time, I thought, this seems kind of like a mess to me. Y is the d squared on top, and the x is squared on the bottom. It doesn't make a lot of sense. And finally, I figured out what it was, and that it's really the following. That when I say this, I'm saying the second derivative of y. In other words, it's the derivative of the derivative of y. How would I write that? Well, it's the derivative with respect to x of the derivative with respect to x of y. So what we do as mathematicians is sometimes we don't want to write all of this, so let's just squish it all together. And when I squish it together, I get, well, it's kind of like a d and a d. Am I multiplying d's together? Not really, but it's more notation-wise. I'm just saying there's a d and a d on top, so let's call it d squared. And then on the bottom, and then there's a y on top. And on the bottom, I have a dx and a dx. So maybe it would make more sense to say parentheses dx squared, but we don't. We write dx squared, saying the whole dx is squared. So this is the notation that we write, and what it means is what I wrote up here. So you can guess now how I would write the third derivative. I might write d cubed y over dx cubed, and so on. So these are 3 different notations for second derivatives, third derivatives, fourth derivatives, etc.